What's up, everybody? We're going to cover a brand new topic called recursion today. There's going to be quite a bit of takeaway from here, so it's not just talking about recursion, but we're going to cover a couple other, you can call them tangents, but they're kind of big takeaways from this programming language. For example, we're going to have a tangent on talking about primitive integers, and then kind of motivating why you might want to use a different type of integer called a big integer. This is a class. It's basically an integer that will let you store arbitrarily big numbers, because the primitive integer doesn't really store as much range. All right, and then towards the end of class, we'll probably talk about stack memory, and some folks might have heard about Stack Overflow. This is a website that people go to when they have some programming problems. But yeah, it's named after something called Stack Overflow, which is an exception that we'll see today. All right, so that's just the outline for today. Quite a bit of takeaways. Let me give some quick announcements real quick before we jump on to the topic. Here we are at the week 15. So we're going to be covering recursion. On Wednesday, we'll be talking about functional programming. This is a very short topic. But coming up next week, we have a final exam. This is going to be on a Monday. It's going to be during the regular class time. All right, it's going to be just exactly like the midterm, except I'm going to replace some of the free response questions. All right, so that's pretty much how I'm describing the final exam. It's cumulative. How I made it was I copy and pasted the previous midterm and replaced the free response questions. Okay, so that's going to be on Monday. And then next Wednesday, I'll give an announcement on this stuff later. But basically, the final project presentations is on a different schedule. If hopefully folks are aware that finals week is a totally different schedule for most classes. You can Google this up, class schedules. You could look up a final exam, I think, at Cabrillo, and then click on class schedules. Your professor should have notified you soon, or will notify you soon, but basically the final exam schedule is right over here. If you have, for example, if you have like a 8 a.m. math class, your final exam is going to be at 7 a.m. All right, but for us, I'm talking about the presentations, by the way. We're taking our final exam a week before the actual finals week. This way, on the last week, we have plenty of time to present projects. All right, so basically, the final project presentations are going to be scheduled for one of these times. Let me just check real quick. So our class is, let me check. When's our class is at 2:40, Monday and Wednesdays. So Monday and Wednesdays, let's see, 2:40. So it looks like our final meeting is gonna be at 1 p.m. on a Wednesday. So this is our very last day, Wednesday, 1 p.m. to 3:50 p.m. Typically we meet for like 2 hours. This one is gonna be for almost 3 hours. All right, I'll give an announcement on this final meeting later. This is a hybrid class, so I think most folks will be asynchronous. Okay. Anyways, so yeah, that's pretty much it. We're almost done with the class. Let's talk about recursion now. Okay, so this is another way of iterating. We've seen for loops, we've seen while loops. Every one of those loops can also be written as recursion. So let me give an outline real quick. Oh, I just talked about this outline earlier. We're not just talking about recursion today. We're gonna kind of go on to some tangents, such as talking about what are the limitations of an integer. We'll talk about stack overflow as well. All right, so yeah, couple little tangents. First of all, I wanted to introduce this math thing called a factorial. So in math, you'll see this exclamation mark sometimes. This exclamation mark means factorial. So if you were to take n factorial, it means to multiply by all the numbers before it until it reaches 1. For example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which equals to 120. So this is a math problem. I wanted to do a quick class exercise to make sure folks can implement this loop. But real quick, I guess we should talk about the concept of this real quick, just so folks can visualize what a factorial means. Basically, it means how many possible arrangements are there. For example, here's a quick visualization. Let's say you wanted to build something and you only have like 3 ingredients. How many different ways are there to arrange those 3 ingredients? Like let's say for a hamburger. Right? For a hamburger, you can have these 3 ingredients: lettuce, tomato, and meat. How many other possible arrangements can we do? Like one, we can have the meat in the middle and then tomato on the bottom. This is another one. And then here's another one. We can have tomato on top, lettuce here, and meat here. Keep going. And we'll find out that there's 6 arrangements, or permutations, as you can call them. Alright, so yeah, this is what it means to take a factorial. This is saying, what is 3 factorial? Right? The 3 factorial is 3 times 2 times 1, which is 6. Right? It gives you all of the possible arrangements. Alright, people cool with this, kind of visualizing what a factorial is? Okay. So let's go ahead and implement this in code real quick so folks can see what's happening. Let's say we do a quick class exercise. Feel free to pause the video if you feel comfortable. But we could do like one way called an iterative method, right? Like how do we calculate the factorial? Well, here the answer is here, but let's say you didn't see it. Let me just pull up this code real quick. So say you didn't see it. How do we calculate the factorial, or make a function, a method, I mean? Okay, here, hold up. Let me formalize this real quick. Let me make an example here. I'll call it factorial.cpp. Okay, I'm pretty much asking folks, so say we have like a main here. Let me put it here. Okay, and I'm just gonna hard code a number, like int. Actually, I'm just gonna call it right away. Say we have a function called factorial, and we give it like some number, like 5. Alright, so this is a method that doesn't exist, but if it did exist, we could expect this to compute 5 factorial. Meaning we can also expect it to return a number. Alright, like say we store into a number, I'll call it like result. And then if we were to print it out, result is result. Okay, so for the class exercise, I'm pretty much asking if folks can implement this factorial method. Meaning that if you were to run the program, it should say 120, because 5 times 4 times 3 times 2 times 1 is equal to 120. Alright, so yeah, feel free to pause the video and try this out. And then I'm going to be going over this iterative method. Okay. So here, let me start this over here. So first of all, this is an integer function method. It needs to return a number. So factorial. All right, and we're not doing any object-oriented programming yet. So these are just going to be some static methods. All right, so let me name this. I'll name it like upper bound. And for now, I'm going to return a dummy value, like 0 here. I'll return 1 actually. This is a dummy return value, just to encourage folks to try it out themselves. Okay, let me compile this. Oh, I just named the CPP for accident. That was my bad. I meant to name this .java. Factorial.java. There we go. CPP is a different language. It's a C++. Okay, let me cd into this directory, cd into examples, and let me compile it and run it. Make sure it runs. It did not run. Let's see. Oh, okay, I just misspelled this. This should have been fact because I'm using a shorthand. Okay, let's test this now. Okay, result was 1. Cool. I highly recommend folks, if you have the time, to pause the video and try this out as a class exercise. All right, basically there is a method you can do. You can do some sort of loop. Right? I did flash a solution here, like a while loop. You could do it in a for loop if you wanted to. It'll be probably cleaner if you did it in a for loop. So yeah, feel free to implement this. I'm gonna continue though. So one way you can implement this is with the iterative method. Iterative means you can expect some number to go within a range. For example, with this, you can imagine we can initialize a result to 1 and accumulate it. Right? Accumulate means to make this number bigger and bigger through a loop. Okay, so one way you can visualize this is keep multiplying them and decrease the upper bound. All right, so you could imagine initialize it to 1, and then on the first iteration multiply both of these numbers and store it back into the result. All right, so then that would give you 5, because 5 times 1 is 5. All right, so it changes to a 5 here, and then we can decrement the upper bound. Right, we can decrement to 4, and then repeat. Right, repeat, like multiply these two again and store it to the left side. All right, so let's do it. So multiply them, we get 20. So store 20 on this side, and then make sure to decrement this over here. All right, so then, and boom, go ahead and repeat. So then 20 times 3 gives you 60. So change this to 60, and then decrement this to 2. Right, and then do it again. So multiply, this becomes 120, and decrement this to 1. Right, and then pretty much you can stop here because the pure definition of factorial stops at 1. Right, there's no need to bring it back to 0. Also, if you did bring this down to 0, it's gonna zero out your answer because 0 times any result gives you 0. All right, so this is one way. You could do it in a while loop. I highly recommend trying to do it in a for loop. This will give you a really good practice, especially for the exam. All right, so let's go ahead and do this iterative method. Let me revert all of these here. Okay. So you could imagine like we have a result variable. Okay, I'm gonna initialize my result variable to 1. You can't initialize it 0 actually, but based off of our approach. If we initialize it to 0, every answer would be 0, because with this result, with this implementation, 0 times anything gives you 0, right? So that's why we initialize it to 1, so we don't lose the data. And once again, one way we can do it is you could do a while loop, where the while loop just makes the result bigger and bigger, and also decrements the upper bound. Right, so we could say make the result bigger, right, by accumulating it, and then we could decrement the upper bound. Right, but the while loop needs to stop at some point. So we could say, do this when it's greater than, when the result, the upper bound is greater than 1. Right. Otherwise, if we got to 0, then it would zero out the answer. And don't forget to return the result here. Okay, cool. So we turn the result, and it should go back down to the main. Okay, let me go ahead and test this real quick. So Java factorial, and we get 120. Okay, this looks good. Let me change some numbers around. Let me try 3. So I'm gonna try a factorial of 3. This should give us 6. It should give us 6, which is representing this over here. So factorial of 3. Let's see. Gives us 6. Okay, cool. Let me try 6 over here. 6 should give us 720. Yeah, cool. Give us 720 because that's 120 times 6. Okay, so we just did the factorial method here. I do want to point out some issues with this though. One is first of all, how big can our numbers get? Like let me try 10. Okay, do people know how big a factorial gets? This is actually a very, as n gets larger and larger, our result gets very large too. So let's see what happens when we get to 10. Okay, so let's go factorial 10, and yeah, we get this. I think this makes sense. You could double check it on a calculator if you want. Or you could double check over here. 10 times 9 times 8. And then yeah, it looks good. Okay, but let's get to 11. So let's go increase it to 11, and then okay, this looks fine again. You can double check it if you want. Let's try 12. Okay, 12 looks good. Yep, see, looks kind of good. Let's try 13. Okay, 13 kind of looks good. Let's go 14. Okay, 14. Kind of weird, right? Isn't this weird for 14? So check it out. I just did 13 here. Let me restart it. People see something weird. So I did 13, and it gave me this number here. And if I tried 14, it gave me this number, which is smaller. Isn't that kind of weird? Let's go 15 here. Let's go 15. Let's go 16 here. And 16 is weird too. Yeah, so at some point we start getting some weird numbers. So if you want to kind of visualize what's happening, well, first of all, the 13 one seemed like it was miscalculated. Let me see. It looks like the 14 one was miscalculated. Let me double check using this calculator here. 14 times 13 times 12 is 11 times 10. Yeah, so it should have been, so 14 factorial should have gave us 87 billion. But give us this. Okay, let me try 13 real quick. Let me see if 13 is right. Well, we're basically going to talk about the limitations of an integer. But let me just narrow down which number is wrong. So 13, let's see what 13 is. 13 times 12 times 9. Oh, okay, wait, 13 factorial give us this. 6 billion. Why did this give us, what is this number here? This is 1 billion. Let me try 12, because it looks like the 13 one is wrong. Okay. There's probably an easier way to do this, so I don't have to type it in every time. Times 10. Okay, let me try 12 here. 12 should give us 479 million. So let's see. Okay, cool. Check it out. Check it out. So this is a 12 factorial. It did get it correct. But when I tried 13 brings us up to this number, which is incorrect, right? Because to get 13 factorial, here, let me multiply this whole thing by 13, and that should give us this number here. This is the actual 13 factorial. It's 6 billion something. But why did we get this number here? This is like 1 billion something. Right? Kind of weird, isn't it? Maybe you want to do some debugging. Debugging statements, like trace this loop. So we could trace this loop to see what's happening. So let me put in a print statement here. Right, the result is currently result. All right, let's study this output here. Okay, let me run this. And for 13, let's see. Okay, so I just ran it, and we can see the result getting bigger and bigger. It starts off at 1, because that's what we initialized it to, and then it becomes 13, because 13 times 1 is 13, and 13 times 12 gives us this, and then it looks like it's doing it fine, but then messes up somewhere over here, I believe. Yeah, it messes up somewhere over here. You see how it's going negative for some reason? Isn't that weird? Why is it going negative? Oh, I think I have the result in the wrong place. Let me move the statement down. Okay, it doesn't matter too much, but I just changed the order of the print statement, and it's you kind of see that something weird happens over here. This is called integer overflow, by the way. So it's kind of like bring us back to week 1. All the way in week 1, we talked about the limitations of an integer. Let me pull this up in a J shell. Okay, so here's the J shell. This will let us do some quick math. Let's say I initialize some number to I'm just gonna initialize some integer to like 2 billion something. Let me pull up my calculator. I'm doing some quick math. Pull up my calculator. Let me see. What is 2 to the 31st power? Let me see real quick. 2. Oh, if you're curious what I'm doing here, I'm on the calculator right now. I'm doing 2 to the 31st power. 2 to 31st power minus 1. Okay, so I'm gonna choose this number here. 2 billion 147 483 647. Okay, so check it out. I'm gonna set a number equal an integer equal to this, and if I did like num plus 1, this gives me something negative. Isn't that kind of weird? All right, like if I did it again, if I reinitialize num to like 1 billion, 1 2 3 1 2 3. All right, you see how num here is a billion, but if I said num plus 1, it gives us the correct answer. Right, this is right. But well, why is this happening? If we set num to this number and we add 1 to it, right, why does it give us a negative number? And if I add 2 to it, right, this still gives us a negative number. Add 3, still negative. Isn't that weird? So yeah, this is back to week 1. Oh, you might recall something called integer overflow. We are using a primitive integer, and primitives are fixed sizes. So in Java, the integer takes, I think, 31 bits or 32 bits in total, meaning that there's a certain range on storing the numbers. It's kind of like over here. Back in week 1, I put up this YouTube video called the binary counter. I think it's called the mechanical binary counter. All right, so a long time ago, I pulled up this video here with this binary counter. Yeah, you can play this later, but basically here are 6 bits, and these 6 bits is binary, and then on the bottom here we see decimal. So the decimal is what we use because we have 10 fingers. So we got 1 2 3 and then 4 and keep going. All right, so here this is an integer. The integer representation with 6 bits. All right, what is the biggest number we can store with 6 bits? All right, well, let's see. There is some math behind it. Basically, the biggest number is 2 to the 6th power minus 1. But let me fast forward it. Okay, so fast forwarding it, it looks like the biggest number we can store with 6 bits is 63. So if we were to add a number here, it's gonna overflow back to the negatives or 0. All right, so people see what it means to overflow. It means we ran out of bits, so all of them kind of flip back to the negatives or the left side of the number line, which is 0 here. So that's what's happening here. We're getting some integer overflow, and also in the factorial. In the factorial here, we ran out of bits. With an integer, there's only 32 bits. So if you go past it, it's gonna go to the negative number line, which is what happened down here. All right. So we're getting some limitations with this. One way you could fix this limitation is by using a different variable. Okay, you could also use a long. People heard about longs before. This is a different type of variable. It basically takes 32 bits. 64 bits instead. So instead of integers, I could change all of these to longs. So let me just change these. Okay, cool. I just changed everything to a long, which is pretty much a integer with double size. And then now if I were to run it, you see we don't get integer overflow anymore. With 13, now we're getting the correct answer. You can verify this on a calculator if you want. I'm pretty sure this is right. All right, but a long also has limitations. With 64 bits, we're gonna run out of room at some point. All right, I'm not sure what that point is, but it's 2 to the 64 power or something. So let me try different. Let me try bigger factorial. Let's go like factorial of 20. Let's see if we can do this. Okay, it looks like we can do factorial of 20 because everything is in ascending order, and it doesn't look like we wrapped to the negatives. So let me see. Let me go 25. Let's go 25 and then run this. Okay, it didn't look like it worked for 25. So you see it kind of overflowed over here, maybe somewhere around here. Right, over here it became negative, so we ran out of room, meaning that all of our answers are messed up in the future. All right, so with the long, this is kind of limited. This is not going to work out as well because, yeah, factorial just becomes really big. Factorial is a really big operation when n gets bigger. Right, like let's say 52. Let's say factorial 52. Do people know what I'm trying to represent here? It's kind of like a deck of cards. A standard deck of cards has 52 cards. So how many different ways are there? Like how many different orders are there in a deck of cards? It's a 52 factorial. But if we were to try to get this, it's going to give us an incorrect answer. Right? It gives us like negative something, which is definitely not right. All right, so we should probably find a way to fix this. This is a kind of a huge tangent, by the way, folks. The tangent here is, well, first we're calculating the factorial iteratively. And then now we're talking about the limitations of this integer. The whole point of today was to talk about recursion. But I think we should go on this small tangent because it's pretty important, especially for a lot of other programming languages. It's not just for Java, but it's also for other languages like C++ does this as well. Python doesn't actually do this because they don't really use primitive integers. They use like a hybrid of an object and a primitive. But yeah, let's go on a quick tangent before we talk about recursion. Okay. So right now with a long, we see some limitations. It might be necessary to use a different data type, and there is a different data type. It's called a big integer. This is not a primitive data type. You could take a look at it. Basically, this is a class that represents integers that are arbitrary precision. Right, arbitrary precision means there can be as many digits in there as you want. Right, you can have like 1,000,000 digits in the integers and you'll still be able to represent it. Right, if you're wondering how, it's basically because this class represents numbers as a string. And not a string. They probably represent it as like a data structure of integers. And the data structure can get very large. All right, so you could imagine it like a string. I would imagine it like a data structure though. So you could use this this big integer. There's gonna be quite a bit of refactoring if you wanted to use this though. So here, let me go ahead and use this real quick. So I'm gonna import the big integer here. Okay, so once again, this is a tangent. Well, I do want to talk about recursion. If you want to get straight to the point, feel free to skip the video, like maybe like 10 minutes, maybe like 5 or 10 minutes, and we'll be talking about recursion. But I did want to talk about this big integer here. Our goal is to not use a primitive, which is this long. Right? This is a primitive because it's fixed size to 64 bits. It would be better if we represented this as a big integer instead. So imagine if we had like big integer result, right? So this is a class that we just imported, and here, let's say, well, so since we're redesigning everything to take big integers, we should probably convert this to a big integer, and the reason why is so we can set this function up to take big integers. So here's what I mean. Check it out. So I want the result to be a big integer instead of a long. So I'm going to replace this. All right, and I also want the parameter to be a big integer as well. Right, this way we can pass any size integers to it. Okay, meaning that we want the result to be big integer. All right, but since we did that, our caller, the main caller, needs to pass a big integer instead of a classic primitive. So somehow we need to represent 52 here as a primitive integer. I mean, as a big integer. And one way you can do that is with their constructor. If you take a look at their class, they have a constructor method. One of these constructors takes a string. So this seems like it's the easiest one to use. So I could use this constructor here by saying a new big integer and then give it a string, 52. All right, so this is a constructor. I'm using this one here. It takes a string as an argument. All right, so let me save this, and then let me go ahead and refactor this stuff up here. Big integer result equal to 1. This is probably not going to work out. Instead, I'm attempting to initialize a variable, but since we converted it to a class, an object, we have to construct it. So instead of a 1 here, you could construct another one. New big integer 1, or you could do this, but I see in the documentation that there's an easier way here. They have a static member variables. So instead of using the constructor, you can just use this member variable or member field, which is you could say something like big integer dot 1. The only reason I knew that was because in their documentation, they represented 1, 10, and 0. Okay, cool. So I'm setting that up, and then I do have to refactor these 3 lines here, because with the upper bound, well, here, let me compile it. I'm probably going to get a bunch of error messages. So yeah, I did get a bunch of error messages. The first one is saying we can't really compare a big integer with an integer. Right, this left side and right side don't match. So there is another way to compare numbers with here. If you take a look through documentation, there's a method called, I think it's called compare to. Yeah, compare to. So we could use this method. Let me pull it up here. Basically, you can invoke the method, compare it to another big integer, and then basically it does all of these operations at the same time. And it does it all at the same time because it returns an integer. and the integer represents whether or not it's less than. All right, so the method will return -1 if it's less than. It'll return 0 if it's equal, and then 1 if it's greater. So pretty much you could represent this as a while upper bound dot compare to 1 integer is equal to some number. Let me look at the documentation here. So if it's greater than, okay, so if the big integer is greater than, then it's going to return 1. Okay, cool. So that means 1 here. All right, so this is saying if greater than 1. I know it's kind of tricky to read here. It actually says if it's greater than 1 because it returns 1 if it's greater than the value. So yeah, it's if it's equal to 1, then that means this whole thing was greater. Okay, and then a couple more things we got to refactor. If you're curious, we have to change these lines because it's still not compiling. It's saying we can't use the multiplication sign. Right, so here it's saying, oh, we can't multiply a big integer by another big integer. We can, just not with the standard multiplication sign. We just have to use an object-oriented style, which is to use this method here called multiply. See this method? Basically, you can multiply 2 big integers, and then it returns another one. So how to use this is you can change this. I'll change it side by side so you see what it does. So you can say result is equal to result dot multiply, and then upper bound here. All right, so now these two lines are pretty much the same. It's that the second line is object-oriented style, and it supports the big integers. And then same with this minus here. See, if we were to compile it, now we have one more error message. It says we can't subtract an integer from a big int. Right, so one way you could handle this is by using another object-oriented. Probably, let's see. There's probably like a minus button somewhere. Subtract, here it is. There's a method called subtract. So you could use this here by saying upper bound equals upper bound dot subtract 1. Right, subtract 1, but we got to represent 1 as a big integer. And one way you can do that is by using their static methods. All right, and then finally, let me change this to an S here, because it's technically representing them as a string. So let me change this D to an S, digit to an S. Okay, let me go ahead and compile it now. It should run. Okay, check it out, check it out. So I just did 52 factorial, and I think this is right. Yeah, I think this is right because numbers are getting bigger and bigger every time, and it doesn't look like they're overflowing to the negatives. So our result at the end becomes like 8 something. It's a really big number. You could fact check this if you want, because this is a pretty popular number. 52 factorial is pretty much saying how many possible ways can you shuffle a deck of cards. So you could look up 52 factorial. And then it says 52 factorial. Is this AI? I can't tell this AI, but it's probably right. So 8 point something times 10 to the 67th power. Yeah, so this is scientific notation, which is representing this number over here. There's like 67 zeros here. Okay, so yeah, this is a kind of a big tangent. It's not too important, but no, it is important actually. It's important when your primitive integer runs out of memory. like because primitive integers can only have 32 bits, which can't store a really large range. So sometimes you want to use a class instead, right? A fancier integer. So you could use this big integer over here. All right. Okay. So let's move on to the main topic of today, actually, which was recursion. So far, we talked about calculating the factorial iteratively, right? Iteratively mean to kind of make the number bigger and bigger. And then we had a small tangent with overflow, right? It's kind of a tangent. It's not really the big takeaway today. But anyways, with that tangent, we talked about big integers. But let's go ahead and talk about recursion. All right, this is this ending topic for today. So another way we could represent the solution is with recursion. Okay, so forget all of the big integer stuff. I mean, you could remember it, but let's simplify it down. Let's say we're working with integers again, just plain primitive integers. All right, so let's say we were to calculate factorial 5. Remember that this is equal to 5 times 4 times 2 times 1. Right, so that would be kind of like an iterative method. Another way you can represent it is by calling the method on itself. All right, and that's what it means to be recursive. Because factorial of 5 is the same as saying 5 times the factorial of 4. Right, does that kind of make sense? Because factorial of 4 is equal to 4 times 3 times 2 times 1. All right, so these two are equivalent. Right, and then you can imagine that factorial of 4 relies on itself again. So factorial of 4 would break down to 4 times factorial of 3. All right, people kind of seeing this, and so on and so on. All right, at some point we do need to stop though, because we don't want to multiply by 0. So there is this ending case here, right? It's called the base case. So the base case here means the function, the method doesn't rely on itself. It just returns a single number. So everything up here can collapse. Right? Because if this kept splitting and splitting, it would go on forever until the negatives. Right? So this is the base case, which makes the whole tree collapse upwards. Okay. So this is a recursive method. It's basically a method that calls itself in the same body. So let me go ahead and implement this real quick. Let's see. I think I'm gonna get rid of this big integer stuff. Yeah, I'm gonna get rid of this big integer stuff. Let me. I'm just gonna comment this out. Yeah, I'm just gonna comment this out. This is the iterative way, iterative method, and uses big integer for arbitrary digits. Okay, so we're gonna do another way. We're gonna do a recursive method. This is the recursive. And I'm just gonna use plain integers, plain primitive integers. It's probably a better idea to use a big integer. I'll let you do that as a lab exercise though. So let's do the recursive method. I'm gonna recreate the main here, and then use some random numbers. Let's say integer. Well, build it backwards actually. Say we have a function called factorial of 5. We can expect it to return an integer. And then let me print it out. I'll just print it out here. Okay, let's go ahead and print that out. So for the recursive method, you can imagine that this is a. Let me set this method up here. Int upper bound. Okay, hold on. Let me just do a dummy return real quick just to make sure it compiles. Okay, it should return 1. Let me run this again. Run. Okay, cool. Cool, so starting from scratch. So with the recursive method, we can just say that this method evaluates to the same method. Right? So we could say call the method and right away return the product of these two things. Right? Because that's technically what factorial 5 is. You just say, hey, factorial 5 is equal to 5 times factorial 4. So you can return it right away. Check it out. So you can just say return upper bound times the factorial of upper bound minus 1. All right, people see what's happening here. Here, let me pull up these slides over here. This is kind of what I'm trying to represent. Let me see if I can pull this. Okay, so this line right here. Let me pull this up. This line right here is the splitting part that I'm talking about. You see how it says upper bound times factorial of upper bound minus 1? That's like right here. Right, so that's what I'm trying to represent. Return this. But the recursion happens because the method relies on itself. Right, so you see how it's kind of circular? It's kind of circular. Basically, this second part is recursive. So this is called the recursive case, by the way. It's called the recursive case because it invokes itself. So you can kind of see the circular thing. If you were to try to run this right now, though, something weird is going to happen. Let me run it. So if you were to run it, we get a bunch of error messages that you can't even read. Like I can scroll up a bunch, and you see how long it's taking me for me to scroll. It's taking me a while. You can drag this up actually. So there's a lot of error messages happening. Can folks kind of see determine what's happening? You can't even see what's happening because the VS Code is limiting my how many lines there are. Let me use a plain PowerShell here, so maybe it has more lines of output. Okay, let me use a plain PowerShell. PowerShell. This is my terminal. Okay. Okay, so let me just CD into here real quick. So CD into what's in my downloads folder? CS-12J. Okay, let me run it from here. So factorial.java. And let's see what's happening. Okay, so I ran it, and yeah, we get a bunch of error messages. I do need to scroll up. So let me scroll up. Okay, so I scrolled up all the way, and something happened here. It says exception in thread, and we get something called a Stack Overflow error. Isn't that interesting? Have people heard of this word before, Stack Overflow? All right, if you were doing a programming and looking up errors, there's a chance that you might have stumbled upon this website called Stack Overflow. It's basically like a place where people can ask questions about their programming projects, and then people in the community would answer them. But yeah, we're getting some sort of Stack Overflow here. Can anyone kind of see what's happening? If you're not sure what's happening, it's definitely something bad. All right, let me maybe do some print statements. So I'll do some print statements to see what's happening. Maybe we could visualize what the upper bound is. So let me say upper bound is at. Let me make this a printf. Okay, so we're doing some debugging statements here, and you know, I'm running in my VS Code terminal, which is PowerShell, but I think the VS Code trims off the top of the lines. Let me see real quick. See, so I got a bunch of error messages, and if I scroll up all the way, yeah, I scrolled up all the way. VS Code is hiding more stuff, so I'm gonna pull up my my plain PowerShell, it might show some more output. Okay, so let me run it in here. This is PowerShell again. And, run it, and then get PowerShell. Let's see, scroll up a bit. Okay, cool. It has a lot more output here. But yeah, people will kind of see what's happening. Let me scroll up all the way. Oh, okay, it ran out here. But hopefully you kind of see what's happening. Upper bound is at negative something. And then at some point, we get a stack overflow. So yeah, for some reason, something happens here. You see how it attempts to print upper bound is at, and it's supposed to say negative something, but instead we get an exception. All right, but basically what's happening here is we didn't handle the base case. So we did a recursive method, but our code currently goes on infinitely, kind of, right? Our factorial of 1 will split up into 1 times factorial of 0, and then it will go negative from there. It'll go 0 times factorial of negative 1, and then it will go negative 2, negative 3. Basically, we didn't handle the base case. So we ended up doing like an infinite recursion. But you can't really do infinite recursion because there's memory limitations. So there's this memory called the stack. And if you were to look at the stack here, if you look up stack memory, this is something you'll learn about in the future. But stack memory is, let me pull up in Java. It's pretty much, actually I'll pull it here. Method calls. Let me see. Function call. Let me pull up the Java one. It's the same thing pretty much, but it's gonna be a little easier to read. So in Java, there's something called a stack memory, and basically this is like a place that Java uses to store method calls. Just one of them, right? And that's what we're doing. We're doing method calls. Specifically, the method is called factorial. So what's happening is we're calling factorial a bunch of times, almost 10,000 times. And those 10,000 times are stored on the stack memory. All right, so the method call information. And we ran out of memory. All right, we ran out of memory. And right over here specifically, we tried to print out a number, but then the Java environment just says, oh, can't do it. We ran out of memory. All right, so yeah, the reason why is literally just because we went down too deep and there was no more memory to keep track of all of the method calls. All right, so you could extend the stack memory. You could say, hey, Java, use more memory. But that's not really fixing the actual problem, right? The actual problem is handling this base case. And one easy way you can handle the base case is by just doing a statement here. Like you could say if we're at the end, then stop here. All right, so you could say if we're at the end, which is upper bound is equal to 1. This is a base case. Just return 1. All right, so this is called a base case here. Basically, it says don't call itself if we reach the end. So return 1. And if you want to visualize that, it pretty much returns 1 at the bottom of the tree, and then everything can finally collapse upwards. That's kind of what it means to be a stack. You see how these methods are stacked together, and they're basically going to collapse in the opposite order, where the down one collapses, and then this one collapses next, and this one, and this one. All right, so here's what I mean by collapse. So here, let me run this real quick. So I ran it, and it's 120. This makes sense. All right, it didn't give us a stack overflow anymore. But basically what's happening here is we called factorial on 5, which calls this recursive case. Right, and then it does that over and over again until we get to 1. But once we get to 1, this collapses, right? So it returns a 1, meaning that this becomes a 1, right? And then the stack collapses upwards. So now that we have these two numbers, this whole thing collapses to 2 right here, right? 2, and then this whole thing collapses to 6. So this becomes 6 right here, and then collapse this, and this becomes 24. This collapses, and then finally this becomes 120. Right, people see what's happening here. So we're kind of collapsing upwards. All right, and that's what I mean to recurse. All right, people cool with this? So this is a recursive method. Every iterative method, like a while loop or a for loop, can be rewritten as a recursive. It might not be appropriate though. Recursion is good for some cases when it's maybe easier to read, or some algorithms are actually easier to implement recursively too. This is just a really small example, the factorial. I'll mention some cool algorithms in the future. But yeah, this is recursion, folks. It doesn't work. It is limited though, because I'm using primitive integers. So you might recall that if I go up to like 20, if I go up to 20, we reach the limits because integers are 32 bits and they can't really store a large range. So if we tried 20, we get a negative number, which is incorrect. For lab time, I would recommend using a big integer. So if you want to do use BigInt, since it can store arbitrary Right, if you want to do this as a lab activity. It's kind of a more advanced thing though. I'm not expecting you to fully do this, but it's good if you want to get into the industry. So yeah, this is that right there. Recursion. Okay, let me see where we're at. Okay, let me talk about some use cases of recursion. This is a really small example. You could use recursion to calculate all possible arrangements of something. So if you had like 3 ingredients, you could pass it to a recursive method that returns all possible combinations. Right? You could do that. Or some other cooler algorithms. I'm not really going to cover in this class too much. If you're going deeper into computer science, you'll probably stumble upon a lot of recursive algorithms. Nowadays, there's AI. AI is a very popular term now. Imagine this right here. You remember your tic-tac-toe game? So you could actually create a recursive algorithm that creates a bot, right? Creates a bot that never loses. So tic-tac-toe. This was an assignment that was delivered like twice. Do people know the optimal strategy to play tic-tac-toe? Well, there's a strategy that makes you never lose, pretty much. And in order to understand that strategy, you pretty much have to look ahead, right? So there's something called the mini-max algorithm, which is basically a way of looking into the future and seeing which route leads us to the best future. So you could create a recursive algorithm that never loses, right? Like a tic-tac-toe bot that either ties or wins. And how you can do that is by creating an algorithm that looks into the future. So here's kind of like a picture here. Let me pull up a picture. So here, you see this top here, you can imagine this is a state. It's a game state. So from here, how many futures are there? Well, there's 3 futures, 3 direct futures, because there's 3 open spaces. So the player could put X here, they could put X here or here, right? But from there are even more futures. there's two futures for each of them. So this is a recursion happening here. It's pretty much saying, look into the future, and then for this future, look into that future, right? And for that future, look further here until we reach the base case. All right, so the base case here is when all of the elements are filled. All right, so this would recurse. It would recurse for all the possible futures. And how the algorithm works is it detects the best base case. All right, so here there's kind of two base cases that would lead to a win. So the algorithm would try to make moves that would steer towards these two cases here. All right, so this is called the mini-max algorithm. You can use it for a lot of games. You can use it for like a chess, for example. You know how when you play chess, you try to look some moves ahead, and it gets really hard because in chess there's like a lot of futures. There's so many different futures in chess. But if you're curious, you could implement a mini-max algorithm. This is kind of like AI topics. So it's something that you'll see further into the future. This is a recursive. It could be represented as recursion. Yeah, once again, mini-max is a way of making decisions. Yeah, making decisions. You can think of it as just look into the future. And if you look at the algorithm here, here's some pseudocode. Pseudocode. All right, so pseudocode is not really like Java code. This is code that's very general, meaning if you can read this, you could apply it to pretty much any language. So this is recursion. So function minimax. This is like saying make a method called minimax, and this method takes a few arguments or parameters, and then we can see the body of this method here. There's like a base case right here, and then there's a large recursive case here. Basically, you can tell this is recursion because it calls itself. Right? You see down here, it's invoking the minimax method, which is itself right here. Right? So this is pretty much saying for each future, right? For each child of the node, right? For each future, look at the futures of all of those. So it's gonna do that and then kind of do a circular thing, which is called recursion. And yeah, this pseudocode is pretty much representing this diagram here. All right. So yeah, pretty cool stuff. It's a really nice algorithm. It's very expensive though. This is a very expensive algorithm because depending on what game you're doing it for or how many decisions there could be like tons, there could be like billions or trillions of futures. All right. So yeah, that's kind of looking ahead. Some good old recursion. Okay, but that's about it. What I wanted to cover today, just kind of scraping the surface. Every iterative method can be rewritten as a recursive method. It just depends on what your style is. Here we just did the factorial, which is formally defined as recursive, I believe. If you were to look up recursion, factorial, and look at the Wikipedia, you'll see the formal definition somewhere here. Let me see. Let me just see this formal definition here. Oh yeah, right here. So this is, if you've taken like an algebra class, you might have heard of piecewise functions. And this piecewise function here is saying n factorial consists of two cases. All right, one is the base case. So this base case is when to stop. And then the second one, this is the recursive case. It's saying it's saying call itself. Right, and itself is this exclamation mark. Remember, this exclamation mark is factorial. So it's saying n factorial is equal to n times n minus 1 factorial. And then it goes all the way down until the base case. So that's right here. Right, that's what I'm representing over here. Where's my piecewise function again? Yeah, so this piecewise function is right over here. Right, the base case is 1, and we got the recursive case right here, just right here. All right, so yeah, tons of stuff, tons of math stuff are represented recursively. Like for example, the Fibonacci numbers, Fibonacci sequence. If you're familiar with the sequence, you'll see that they also define it recursively. All right, but basically I'm not going to talk too much about the Fibonacci sequence, but basically it relies on the previous numbers. And yeah, this one here, they're defining it by this recurrence relation. Right? Recurrence relation is recursion. And they're saying the base case, right? There's two base cases. The first two numbers are 0 and 1. And then the next numbers are based off of the previous one. So that's recursion right here. I'm kind of making some Fibonacci numbers. All right, tons of base cases. You can do it in, for me, I just did mainly AI algorithms. I remember spending quite a bit of time implementing this expect-a-max algorithm. Expect-a-max algorithm, which is kind of like the mini-max one. If you're curious, it's not really part of the class, but if you know how to implement these recursion algorithms, you could create bots. Create bots that can look into the future and beat any human pretty much. Okay. Yeah, so that's about it for today, folks. The recursion. At a high level, we really just did the factorial. We did it iteratively, which I commented out down here. We did it iteratively, and then we found out that there were limitations of integer. Specifically, integers are fixed size, and sometimes we need more. So we talked about big integer, which is a fancier integer. It basically allows you to store arbitrary digits, so you're not stuck to 32 bits. And then later on we talked about recursion. We did recursion up here using primitive integers. I would recommend using a big integer, this just so we can have more flexibility. And then also briefly talked about stack memory. Sometimes when your program gets bigger and bigger, you could end up having stack overflow. And one way you can fix this is by allocating more stack size. I forget exactly how you do this, but I think you can just give it a flag. I think it's like dash something something. I think it's dash SS for dash stack size. And then I think there's an X in here because that configures something. And then give it some numbers here. Say like 2 megabytes or something. And then your name here. Name of the class. I think this is how you give it stack size. I gotta look it up. But yeah, you can basically run your Java program and give it a command that says, hey, use more stack memory. But that's kind of like a band-aid fix. I mean, you might want to look into the root of the problem and maybe see if there's ways on optimizing. All right. Okay, so that's about it for today, folks. Let's end it here, and then Wednesday is going to be a really short topic. It's going to be talking about functional programming. Next week on Monday, there's going to be a final exam. It's going to be on May 11 at 2:30. I just published it somewhere over here. So let me publish it here. Yeah, so this quiz is locked until May 11. I'll post an announcement on this later. It's basically going to be just like the midterm, but the free response questions are replaced. All right. Thank you all for being here, folks, and I'll see you all again. Bye-bye.